You've felt this force your entire life, but you've never actually seen it. It's this mysterious power that can reach through empty space, pull things together, or push them apart, all without ever touching them. It's what makes our motors spin and even protects our entire planet. So today, we're going to make that invisible force visible.
Just look at this. It's this beautiful, almost artistic pattern made from tiny little flecks of iron. But they aren't just arranging themselves randomly. No way. Something is guiding them, sculpting them into these really elegant curves and lines. There's an unseen blueprint at work here.
So that's the big question, right? It's a simple one, but the answer is pretty amazing. What is this invisible force?
Okay, let's get right to the source of this whole beautiful mystery. It all starts with something you've probably played with a million times, a magnet. Now, a magnet isn't magic, it's just a special kind of material. And its special property is that it can attract certain metals, things like iron, steel, nickel, and cobalt. And here's the deal. Every single magnet, doesn't matter what shape or size it is, follows one fundamental rule. It has two ends, which we call poles, a north pole and a south pole. Now, if you put a north next to a south, they snap together. They attract. But if you try to push two norths together or two souths, they'll literally push each other away. They repel. This simple idea, opposites attract, likes repel, is the key to everything else we're about to see. But here's the thing. A magnet's power isn't infinite. It can't just reach across a room and snatch a paperclip. Its power only works inside a very specific, invisible boundary. See? If a paperclip is too far away from the magnet, well, it's just a paperclip. The magnet is right there, its power is on, but because the paperclip is outside that special zone of influence, nothing happens.
But watch what happens as we just shrink that distance a little bit.
And snap, it gets pulled right in. The second that paperclip crossed into that invisible zone, the force just took over. So that invisible zone the paperclip just entered, well, scientists have a name for that. It's called a magnetic field. It's basically the area all around a magnet where its force can be felt, or, as we just saw, detected. And this is super important. This field isn't the same strength everywhere. The force is always concentrated and most powerful right at the north and south poles. That's exactly why you see stuff cling so tightly right to the ends of a magnet.
Okay, so if this magnetic field is totally invisible, how in the world do we know it's even there? And an even better question, how can we possibly figure out its shape?
Well, there are two really simple ways. The first is what we just did with the paperclip. You just see if a magnetic object moves when you bring it close. The second way, though, is a bit more clever. You use a compass.
And this is such a cool way to see it work. The needle of a compass, it's actually just a tiny, lightweight magnet. And when you bring it inside a magnetic field, that little magnet needle will pivot and turn until it lines up perfectly with the direction of the invisible force. It literally points the way the force is going. So by using tools like compasses and just observing these forces, scientists figured out something amazing. They realized all magnetic fields follow a clear set of rules, which lets them create a kind of blueprint for this invisible force. And it all boils down to just a few key rules for mapping out any magnetic field. Rule 1. The lines always connect the north and south poles. Rule 2. They have a direction. Think of them like one-way streets, always flowing away from north and toward south. And finally, the lines never, ever touch or cross over each other. They always stay in their own lane. Okay, so if we take those rules and apply them to a simple bar magnet, what kind of blueprint do we end up with? We get this. These beautiful, sweeping arches flowing out of the North Pole and looping all the way back around into the South Pole. It follows all the rules perfectly. All right, what about a different shape? Let's use the exact same rules, but this time on a horseshoe magnet. Whoa, okay. Because the poles are now facing each other, you get something totally different. You still have those big arches on the outside, but look at the space between the poles. You get these incredibly strong, straight lines shooting directly from north to south. That's where this field is most intense.
And now, this is the coolest part. This is the big payoff. On the right, you have the blueprint, the drawing we made just by following those simple rules. And on the left, those are the real iron filings from the very beginning. Look at them. It is a perfect match. Our abstract rules predicted the real-world pattern exactly. We made the invisible visible.
And this blueprint gives us one last, really crucial piece of information. How can you tell where the field is the strongest? It's simple. You just look for where the lines are packed most closely together. The denser the lines, the stronger the force. It really makes you wonder, doesn't it? If these invisible blueprints, these lines of force, are powerful enough to control something as simple as a paperclip, what else in our universe do they control? From the way data is stored on our computers to the giant magnetic shield that protects our entire planet from the sun, these same invisible rules are at work everywhere.